Okay, everyone, so it's time to start, and you probably all heard that classes are canceled tomorrow. So if you're, we don't have class tomorrow, but if you're in one of the sections, online people who are watching or go to the sections, you don't have class tomorrow. So it's great we have this system for people in those sections because they can watch this lecture, which will be what you would have covered on Wednesday. So let's look at the calendar now, and let's see what's due. So right now, tomorrow night, you have homework 4 due, and it's a really pretty long homework. It covers chapters 5 and 6. We're going to finish 6 today. So you could have already done most of this, and I see a lot of you have, but give yourself enough time to do this. It's due tomorrow night, Wednesday night, at 11:59 p.m. So allow yourself more time for that one. And then we have all these pre-lectures due and a survey due. Everything's up except for pre-lecture 10 and bonus survey 2. So you can, those are fun and they're easy, really easy, these pre-lectures. I strongly recommend you doing them even if you don't need the bonus points because they just give you a really basic understanding of what's going on. All right, so today we're going to finish up chapter 6 and do 7 and 8. So any questions before we start? You know, my hand is so cold. I fell on the way yesterday and now it's numb. This hand is numb. This left hand. I think it's very odd. It's a terrible sensation. Thank goodness I'm a righty. Okay, so now let's go to the document camera. And let's look. So today's the 29th, and this is where we left off on page 40. So, and this is just like a homework problem that you have. If you haven't looked at it yet, this is very similar. So it says, suppose jurors make the right decision about guilt and innocence 95% of the time, and that 80% of all defendants are truly guilty. So as I said before, when you have two conditions and do these conditional probabilities, the simplest way is to make a table. And it's easiest to start with these totals here. So usually you'll give how many people total, but I'm just going to write 100 if you're not, just because it's easy to work percents out with 100. So out of 100 defendants, we can fill this in with 80% are truly guilty, which means, so 80% here are truly guilty at 80% of 100. So I don't have to put the percent in, I'm just doing the numbers. So 80 out of 100 are guilty, which means 20 are innocent. And this is just, suppose. I didn't model this on anything, necessarily true to life. So let's say that 80 of them are guilty and 20 of them aren't. Now, what other information do we have? What does this say? So this says 95% of the time they make the right decision. So this is saying that basically there's 95% of the time, if this was a medical test, it would be 95% of the time there's true positives, 95% of the time there's true negatives. They only make mistakes 5% of the time. So what's the correct decision is if you're innocent, the correct decision is to acquit. So 95% of the time they're going to correctly acquit these 20 people. So that means that it's 19 of them are going to get correctly acquitted, which means 1 out of the 20 will get, unfortunately they're innocent, but they'll get convicted. And that happens, right? These, we all know these jury trials we're making a decision under uncertainty, and obviously it's not always correct. So 95% of the time. Now, what about the guilty people? If they're guilty, the right decision is to convict them. So 95% of the time, these 80 people will get correctly convicted. So there'll be 76 will be convicted. So that's like we're correctly doing that, but then there's 4 mistakes right here. All right, so because these have to add up. So it's always important to do these totals first. So do this column first on your homework. It's good advice. All right, do this column first. All right, so now we can add these totals. So we get 23 here, and we get 77 there. And by the way, I think, okay, let's just keep going. All right, so what's the probability that a person is convicted given that they're innocent? Given that they're innocent. So what we want to do is what? Convicted given that they're innocent. So if we look at the innocent people right here, how many of them are convicted? 1 out of 20. So this is the probability of convicted given, that means given, innocent. And that's equal to 1 out of 20. All right, and now what's the probability that a person is innocent given that they're convicted? So now we're looking at all the convicted people. Given that they're convicted, what's the probability they're innocent? Okay, so this is the probability of A given B and the probability of B given A. And we saw last time they're not necessarily the same. In fact, they're usually not. So this is what? Out of the 77 people who are convicted, given they're in this pool, only 1 out of the 77 is innocent. Okay? So even though it looks like, when you first read this, you probably think, oh, 5% of the time they make a mistake, so that's going to be 5% of the innocent of the people in jail or people convicted. You're going to think 5% right here, 1 out of 20, are going to be wrongly convicted. But you have to consider that in this population, only 20% of them are innocent and 80% are guilty. So that's why this isn't the same. So it's not as bad a situation as you might expect. You know, you'd hear this, you'd say, oh, 5%, but no, only closer to 1% are really, if it's this situation. Okay, do you understand that? We talked about that last time. All right, so now, and in your homework, you're going to have, okay, well, you'll see when you do the homework. All right, so let's move on to these medical tests, to another medical test. And this is one that's was the most common medical diagnostic test to see if people carry the AIDS virus in their HIV, in their blood. So for years, ELISA has been the most widely used test for screening donated blood for AIDS. So, and this is how ELISA worked. So if a blood sample has the AIDS virus, then there's a 99% chance, that sounds really good, 99% chance that ELISA will correctly give a positive result. So there's only 1% false positives. And if the blood sample does not have AIDS, then there's still only a 6% probability, only 6% that it will incorrectly give a positive result. Okay? So 94% of the time it's correct when you don't have AIDS, and 99% of the time it's correct when you do. So and then you're given one other piece of information that's very important, and that's this. About only 1% of the blood samples ELISA tests are truly contaminated. All right, so now the question is, let's say you got a positive result, which would be really scary. You got a positive result, you're just donating blood, right? And here all of a sudden they call you up and they say you've got a positive result. What's the chance that you have AIDS? So just intuitively, how many people would think that given a positive result that you know, it looks like such a good test, 99% and only 6% false positives here. What do you think the chance is that if a random person who gets a positive result really does have AIDS? Raise your hand if you think it's over 50%. Raise your hand if you think it's under 50%. So most people would think that it's, with this, if you intuitively ask even doctors, they would say it's pretty high probability that because it's such a good test. So how many people think it's like under 20%? Can anybody intuitively just know what it is? Well, here, I can show you intuitively a good way to think about it, and then we can fill in the chart. A good way to think about it is, let's just look at this. So what we're trying to figure out right here is if you get a positive result, this one, what's the probability someone has the AIDS given they tested positive? All right, so let's just start with 100 people, right? And out of 100 people, how many of them are actually going to have AIDS and how many aren't going to have AIDS? Well, you have to look at that 1% right here. So out of the 100 people, one would really have AIDS. So one person has AIDS, which means 99 people don't have AIDS. All right, so now this one person has AIDS. So there's a 99, this is a really good, if you have AIDS, there's a 99% chance that probability that you'll correctly get a positive result. So this person, 99%, this person most likely got a positive result. So this person will have, so we have one true positive here. 99% of the time. So we can be pretty sure we have a true positive here out of 100 people. But now out of these 99 people, 6% of them are also going to test positive. So 6% of 99, it's like 6% of almost of 100. It's very close to how many? How many are going to get false positives? 6. So 6 of these are going to get false positives. 6 out of the 100 wouldn't. It's almost 100. So we have 6 false positives here. So this means altogether, how many do we have? We have 7 positives total. 7 out of 7 positives, right? But there's only one who really has AIDS. So one has AIDS out of the 7 positives. So there's one true positive out of the 7 total positives. So this is about 14%, 14.3%. So it's less than 1. So your chance is about 1 out of 7. And the picture would be what? The picture to think about this would be that, all right, we have two things. We're looking at testing positive. So this is the probability of having AIDS if you test positive, right? That's what this is. And then there's also the probability, no, this is a probability someone has AIDS given the person tested positive. And then there's this other probability here, which is the probability of what? The probability that someone tested positive, the probability they tested positive given they have AIDS. And this one is 99%, right? This is 99%. But this one is only about what? 14%. And why? Let's draw the picture. So there's two events here. One is the probability of testing positive, which is much bigger. That's testing positive, right? That has 7 people out of a big sample size, right? Out of the whole sample size, 7 out of the 100 test positive, compared to this, the probability of AIDS, which is only 1 out of 100. And almost the AIDS, so it's like 1/7 this big, and there's a tiny little fraction of it. So this is the AIDS. And almost everybody who has AIDS will test positive. There's just one tiny little percent outside that. So if you test positive, only 1/7 of the time would you have AIDS. Because these two events aren't the same size. Remember what we said last time? The only time that those two would be equivalent is if, this is A given B and B given A, is if A and B are the same size. And this is much smaller than that. All right? So that's the idea. If we wanted to do it exactly out of 100 people, we'd say what? So out of 100 people, we know that 99%, that's 1, has AIDS, and 99 don't. And then we know out of that 1, we're looking at this 99% here, out of 99%, 0.99 of that 1, which is 0.99, tests positive, right? So that means only 0.01 tests negative. And then out of this 99, we said, out of the 99, it's going to be 6, but it's not going to be quite 6. It's going to be 0.06 out of 99, which is just a little bit less than 6. That's 5.94, which means what? Which means to add up to 99, it's almost 93, but it's 93.06. So then when we do these totals here, we said the total number of positive is 7, but it's, if you want to do it exactly, it's 6.93, almost 7. And here, this adds up to 93.07, and together they add up to 100. So what I'm saying here is if you were doing the probability of positive given AIDS, you'd have, given that they have AIDS, which is 1, 0.99, which is 99%. And then, what's the probability someone has AIDS given they tested positive? Well, out of the 6.93, 0.99 tested positive. And if you do that, you're going to get very close to 14.3%. So these two are the same. Okay? Any questions on that? Does that make sense to people? So this comes up all the time with rare diseases. I faced this problem myself with mammograms. I was told that I tested, I got a positive result, and I was even scheduled for surgery, and it was very scary. It was like, and I said, well, wait a sec. This was a few years ago when doctors, it wasn't that long ago, but they weren't that familiar with this. They probably still aren't. So I had to, being a statistics person, I did the research myself and realized that my chances were very small, even though they told me that it was a very good test and I probably had to schedule surgery for breast cancer. And it turns out, of course, it was a false positive. Not of course, but it was overwhelmingly. I mean, they're supposed to, so make sure that you get tested again. Okay? All right. So that's the idea. And this is something, this is a very, this has a way to figure out the probability of A given B from B give the probability of B given A and vice versa is called Bayes' rule. And that's the basis of a branch of statistics that's really important called Bayesian statistics. All right. So, so basically the Bayes' rule, all right, is based on, and we know that the probability of A given B is equal to the, what is this? This right here is the probability of A and B, right? The probability of A times the probability of B given A. So that's just the probability of A and B, and this is over the probability of B. So it's the picture, it makes sense that that's what that is. You have a picture, you have A, and you have B, whatever it is, and A and B is the intersection. So the probability of A given B means that if you're in this circle here, in B, given B, what's the chance you're also in A? So that's why that rule makes complete sense. Once you know your B, given B, you know that this little intersection here over this equals the probability of A given B. All right? And so if we wanted to do the same example using Bayes' rule, the probability of AIDS, being AIDS could be A, given that you test positive, is just this, and that's the probability of AIDS right here, and that's 1% times, so this is the probability of the numerator here, but this right here is hard to figure out, the probability of positive. So there's another formula. What's the probability of B? So you usually don't know that directly. So this is why there's another rule. And it looks very complicated. This is really how you see Bayes' rule, but it's not that hard. Let's just put it in our chart here, and let's just do the approximation. I think it's a lot easier. Okay, and you'll see where this fits into here. So, so you can understand this because it looks intimidating. So remember, we have 1% has AIDS, so we have 99 here. And then we said, okay, so 0.99, well, 99% of those will test positive, and 0.01 will be negative. And then we said, okay, 6% of these, so we said 0.06 of the 99, and let's just do this approximately, make it easier, 6. So this is, right? And so this is approximately 93. They add up. And this is approximately 7, 1 plus 6, and this is approximately 93. Just so you can figure it out here. So what are we doing here? So this right here, this is 1%. Here, I can just write it so you can see where it fits in. This right here is 99% of that 1, which is 1%. 99% of the 1%. So you can think of the numerator, this right here, being this, and then, or this, right there, that's like that. And then this is the same thing, right? The probability of B, these two are the same. And then you can think of this one right here as this. And then together, so what are we getting? So we're saying, so this is approximately 1, and that together is approximately 7. That's all that really boils down to. And what's here? The probability of this denominator right here is this 7 over 100. That's where that comes in. Okay, so that, this right here, should have another color. This is this over 100. And you have to divide, I guess, yeah, this over 100 too, to get that numerator. It's like out of the 100 over this out of the 100. Okay? So that's the idea, and it's going to come up a lot. So in the, you can do these problems with a chart, and I think it's always important if you don't understand this to just do a simple chart, because it's just hard to keep all this language straight. But in more complicated problems, you really need to know, you have to think about this, and it really is important because you're going to be seeing this. It's the basis of a whole branch of statistics. It's becoming increasingly more popular. Okay? So it will be really handy to understand it and to know that too. But I'm not going to test you on this, just on the tables. So any questions on that? And I'm sure some of you have already know a lot about Bayesian statistics. But all right. So this is the summary. And again, I say always pay a lot of attention to these summaries. Always read them. And what we talked about today was this. But remember what we talked about before about how sometimes, so this is like the complement, something not happening, plus the something happening, the probability of A plus the probability of A complement is equal to 1. Not happening. That's very useful when you can't figure out the probability of something happening directly, when it's like hard to figure out, like this one. And this one is hard, so you use the complements, 1 minus the complement. All right, and the multiplication rule we looked at, and that's the probability of two things both happening, we just drew the picture, is the probability of 1 times the probability. Now, so like when you think of it, the probability of A plus B, people think, oh, that's A plus B. That should be the probability of A plus the probability of B. No, it's going to be the probability of A times the probability of B, given that A happened. And so these probabilities gets, the probability of both A and B happening, as we saw, A and B, that's this. It's the intersection. So the probability of A and B is the same thing as the intersection, and it's smaller because you want both of them to happen, right? The probability of, finding a husband that's rich and good looking is smaller than the probability of finding rich or good looking, right? And each time you add another thing, rich, good looking, nice, he likes you, then it gets smaller and smaller and smaller, and pretty soon you can't find that person. That's, right? Just putting it in the context of something we care about. All right, so that gets smaller, your probabilities. Whereas if you say rich, good looking, or nice, or, he cares about you, or, eventually you'll find somebody, because if it gets bigger and bigger and bigger, that's lots more possibilities. And that leads us to our next chapter, which is the addition rule. The probability of two events, one event happening or the other. You add the probabilities. That's the union. Okay, the probability of an outcome. All right, so we're going to talk about the addition rule. But first, let's remember our definition of probability. It's you look at all the outcomes, the total number of possibilities, and that's called the sample space, remember? And then we count the number of ways that what we're interested in could happen. That's divided by, so that's the number of, that outcome, whatever outcomes you want, the number of that outcome. I just write it again, sorry. Just repeated that over the whole sample space. So here's a good example. Sometimes this is the easiest way to figure things out when we're adding probabilities. And then we're going to look at how the probability, the addition rule, by the way, is going to be, this is going to be the probability of A or B. That's what we're going to add. It's going to be the probability of A plus the probability of B minus, what do you think? Let's just do it. And then this is where we're leading to. You have A, there you have B, and now A or B is going to be all of this. That's the probability of A plus all of that. But look, we don't want to double count that little piece there. That's part of A and B. So it's minus the probability of both, or minus the probability of A and B, minus the probability of both, the intersection. So that's a much bigger chance, much bigger chances. You have all of that, and all of that, you're just going to subtract off that little thing. But first, let's just go back to our sample space definition. And so we're just looking at what's this example say? 2 dice are rolled. What's the probability of getting a total number of 4 spots or 7 spots? All right. So let's think about it. So what's our sample space? Do you see that it's all 6 times 6 possibilities here equal to 36 possibilities? Because you can think of it as on the first 2 dice are rolled, or 1 die is rolled twice. So the first die, you can think of it as it could fall on 1, 2, 3, 4, 5, or 6. And then you can think of this one as the second die, and it can fall all on 1, 2, 3, 4, 5, or 6. So let's say your first die falls, you land with 1 spot. Well, then you roll it again, and you can get a 1, 2, 3, 4, 5, or 6 on the next one. Same with 2, etc. So it's 6 ways the first can fall times 6 ways the second. So out of the 36 ways, what's the probability that they sum to 4? So the probability that you get a sum of 4 is going to be what? Out of the 36 ways, you're going to count. Well, how many ways are there to get a 4 on here? You could probably see, you can think, well, you could get a 1 and a 3, and then a 3 and a 1. Those are two separate ways. 3 and a 1, these two, this one and this one. But then you can also get a 2 and a 2. And of course, you don't want to count that one twice because there's only one way you can do that, 2 and a 2. See? So it's a 2 and a 2. So there's 3 out of 36. Okay? Or 1 out of 12. You can just leave it this way on ln kappa. It's fine. So now what's the probability of rolling 2 dice and getting a 7? So do the same thing. Sum of 7. So out of the 36, you can think, okay, 1 and 6, 6 and 1. 2 and 5, 5 and 2, 3 and 4, 4 and 3. And you can see it's really right along here. There's the most ways, there's 6. So that's the single most likely possibility. Okay, when you look for 8, you can see 6 and 2, 5 and 3, 4 and 4, 3 and 5, and 2 and 6. And you can see there's 5 ways to get an 8. And there's also 5 ways to get a what? An 8. And there's 5 ways to get a 5, 2, 3, 4, 5, 6. Okay, so the probability of a sum of 8, I'm not going to write them all down, but you can see there's 5 ways. You can count them right here. Any questions on that? All right. So now we're going to look at just what I told you here. And, okay, so we looked at the multiplication rule already. That's the chance that two things can both happen. And I tell you, it narrows it down, right? You have to look at the intersection of them all. And now we're going to look at the addition rule. And that's what we just did. Okay? So we can just say the probability. So when you add, you multiply here. You don't put a plus sign. I know it seems like anti-intuitive, but just remember the picture. I'll just draw it again. You have A, and you have B, and it's just you want them both to happen, so you got a smaller. Remember, these are fractions. You take a fraction, you multiply by another fraction, right? So it's really, we should say, this is the same. This is only when they're independent. We want, the general rule is the probability of A and B. You multiply. It's the probability of A. Whoops, look at this. A and B. So it's probability of A times the probability of B given A happened. That says probability of A and B. See, this was left off because I said if two events are independent. So if they're independent, the probability of both, okay, so the probability of both is 0. They're independent, so there's not an intersection there. Okay? So because, so you don't have to, when they're independent, maybe we should remember, when independent, what do we have? The probability of B is, oh, sorry, I'm making it so messy. It's not, shouldn't be hard. I'm saying, when independent, the probability of this B given A, the probability of B given A is the same as the probability of B. Because when they're independent, remember, B doesn't care if A happened before. Makes no difference. So when independent, the probability, and that's why when they're independent, those two are the same. All right, so now we got the addition rule here, and it's the picture we saw before. So now it's A and B. And we just don't want to double count it. Maybe I should draw it like this, all of that, and this, all of that. And where they cross over, right there, you have to subtract that off, right? So minus the probability of both. That's that part. So there's the probability of A, there's the probability of B, and you're minusing both. Okay, now if they're mutually exclusive, so you call this right here, this is the probability of A and B. And that's the same as the intersection of A and B. A intersection. It's going to be on the next page, what an intersection means. So A intersection, that part. And now we have A or B, the probability of A or B is equal to A union B. You're uniting them, but you don't want to count those twice. So that's why you subtract that part off. But if they're mutually exclusive, I'm going to put it over here. If they're mutually exclusive, another word for that is disjoint, mutually exclusive and disjoint, what does it mean? It means that the picture's like this. There's A and there's B. And if A happens, it excludes the possibility of B. So when you have the union here, the probability of A or B, you can add them because when they're mutually exclusive, because what? Because the probability of them both happening is 0. So when you minus both of them, that, because the probability of A and B equals 0. So it boils down to that. That's mutually exclusive. There's no overlap. So then it's just super easy. It's just the probability of A plus the probability of B. It's still the union, but you don't have to worry about subtracting off or double counting. All right, so let's see. Here's an example. So let's say, pick a random person in this class, enrolled in Stat 200. What's the probability that the person is either in Stat 200 online or Stat 200 in person? So that's the probability of online or in person. Is there an overlap? That's going to be the probability they're online plus the probability they're in person. And you're not supposed to be able to register for both, so you can't be in both, okay? So it's just this one's mutually exclusive. Unfortunately, this isn't true now. For some reason, they messed up and people have been registering in both. But you're not supposed to be able to be in both. Okay? You're either supposed to register for one or the other. But let's say, pick a random person in Stat 200, and what's the probability that the person is online or female? Well, of course you can be both. So that's going to be the probability of online plus the probability of female. And if we didn't subtract off, like about half, more than half the people are online, and more than half the people are female. And so if we didn't subtract off, we'd get over 100%. So it's minus the probability of both. You got it? All right. So any questions so far? Oops. So here's the picture. So we can just do this with the one we just did. This could be the online, and this is females. And right here is both. So there's an overlapping. So they're not mutually exclusive. Where here, they're mutually exclusive. And here, they're not mutually exclusive. Mutually exclusive or disjoint. Either way, you'll see both terms used. And here, This is online, and this is in person. You're not supposed to be, can't be in both. All right, and so this is intersection. We already talked about that, intersection and union. All right, I think we can almost, let's do some examples. So what's the probability of getting either a 5 or a 6? 5 or a 6 on one roll of a die. So we're going to say the probability of a 5 plus the probability of 6. And now do we need to subtract anything off? Can you get both a 5 and a 6 on one roll? No, they're mutually exclusive. Are they? Yes. Because why? You can't get both on one roll. You could on 2 rolls, but not on both. Okay? So what would be the answer? 1 6 plus 1 6, which is equal to 2 6. Okay. These are the same. These are really easy. You can do this. This is mutually exclusive too. Let's just do this on 2 rolls of a die. Let's look at what happens. I think it's on the next page. I hope it is. Yeah, let's continue. So what if there's 2 rolls? What's the probability of rolling a dice twice and getting either a 5 on the first roll or a 6 on the second roll? Now we have the probability of a 5 or 6, but now both can happen because you can get a 5 on the first roll or a 6 on the second roll. So now, when we look at this, are they mutually exclusive? No, you can get both. So now what are we going to do? Now we're going to say the probability of a 5 plus the probability of 6. This is not mutually exclusive. So it's going to be minus the probability of both. So how would we do that? You'd say 1 out of 6 times you're going to get a 5 on the first one, plus 1 out of 6 times you'll get a 6 on the second one, minus what's the probability of both? 1 6 times 1 6. So you have 6 out of 36 plus 6 out of 36 minus 1 out of 36. So your answer is 11 out of 36. Another way to see this would be to think, let's go back to our see picture on page 43. So let's do that. All right. So we said a 5 on the first roll. Well, that's all these. So we could say that's 6 out of the 36, the probability of getting that. And then a 6 on the second roll. That's another 6 out of 36. And do you see how you double counted this 5, 6? You counted it both as a 5 on the first and as a 6 on the second. So there's the 1 out of 36 where you have to subtract off. So that's a more visual way to see the same thing. And let's write that down. So see picture, and you come up with the same problem. And you'll see, so if you do see picture, you'll do the same thing. You'll say 6 out of 36 plus 6 out of 36 minus 1 out of 36. And you get the same thing. That's the same as 11 out of 36. So there's one way to do it, and then there's another way. And they're the same. All right. So I always like to look at pictures. It really helps me, especially with probability. The more pictures I see, the more visualization of it, it makes it so much easier for me. And for probably a lot of you too. Okay. So now let's see, what's this one? What's the probability of drawing a card from a full deck and getting either a heart or a queen? Either a heart or a queen. So we want the probability of a heart or a queen. So are the two events mutually, if you get a heart, does that mean you can't get a queen? Can you get both? Yes. So they're not mutually exclusive, because what can you get? Because you can get the queen of hearts. So the probability of getting in a deck, the probability of a heart is 13 out of the 52, plus the probability of a queen is 4 out of the 52, minus the probability of both. You can multiply those together, but you can probably realize it's just 1 out of 52. So it's 16 out of 52. And the picture would look like what? So the picture would be the hearts are bigger. There's 13 of them. And your sample space is 52, so you could draw it out of the 52. And then you only have 4 queens, but only one of them's in there. So these are the 4 queens. And right here, the one you're double counting is the queen of hearts. And they're all in the sample space of 52 cards. Okay, so that's where this comes from. All right. And so 3 of them aren't hearts and 1 of them is. What else? Here, these will be good practice before we move on to the last chapter. And this is those 2 cases, remember, where it's hard to figure out. The probability of at least one and the probability of not all. So let's remember this. So what's the probability of getting at least one, what does it say? 1 5 on 6 rolls of a die. Okay, so the probability of at least 1 5. All right, now this is a case where adding up the probabilities, remember I said it's really complicated, it's going to be really hard, because at least one, what's our sample space here? You could get 0 5s. Where can I write this? So you could get 0 5s. You could get 1 5, 2 5s, 3, 4. How many times are we doing this? 6 rolls. 3, 4, 5, or 6 5s, right? Now at least one is all these. Those are all at least 1 5. And this is none. None. Now, if you were trying to do it by the addition rule, you'd have to add them all the ways you could. This would take you forever. But this is so easy. This is the complement. So we're going to say that together they have to add up to 1. So the probability of at least 1 is 1 minus the probability of none. And it's so much easier rather than trying to use that addition rule. So it would be 1 minus. Now, take it one at a time. How many ways are there not to get a 5 out of the 6 faces? There's 5 of them, right, that aren't 5. 1, 2, 3, 4, and 6. So there's 5. And then it's 6. You want it to happen 6 rolls, so it's raised to the 6th. So that's your answer. And you can leave it in that form. And we can do the same thing with not all. So what's the probability of rolling a die 3 times and not getting all 2s? Not getting all 2s is going to be hard. All 2s is easy. There's only one way that can happen. So the picture for not getting all would be what? Not getting all. You'd have, what's your sample space here? 3 times. So you could get 0 2s. I can write it out better. You could get 1 2, 2 2s, or 3 2s. And what we want, not all. So this is all right here. And all of this is not all. So we'd have to add all this up, and that's hard. So let's do this. So the probability of not all 2s is equal to 1 minus the probability of all. So that's 1 minus. Now, out of the 6 faces on the die, only one of them is a 2. So all Getting a 2 on the first is 1/6 times 2 on the second times 2 on the third, so it's raised to the third. So that would be our answer. Any questions on that? All right, so that's our section on probability. My hand is still numb. Oh. All right. And here's our summary. All right. So what are we going to do now? The box models the expected value and the standard error. So we're starting a new part here. Statistics for random variables. So what are random variables? We haven't encountered them yet. So far we've been looking at statistics for lists of numbers, the numbers given to us. Now we're going to look at statistics for numbers that vary. They're numbers generated by a chance process. So that's why we did some probability, because we are going to do simple probability models and look at the numbers generated by them. This is so that we can do inferential statistics, inferring about a larger population from a random sample. But we're going to start off in a much easier direction where we're going to know the population and we're going to look at all the possibilities of numbers and that we can get generated by that probability model, and what we'd expect to get, the expected value, because it's like an average, but it's an expected value. We don't have a list of numbers. What will we expect to get in our sample? What is the variability around that? That's like the standard deviation, but now it's for a chance process, so we call it the standard error. And then we're also going to look at distributions of all look at all possibilities and assign probabilities to them. So we'll look at probability histograms for random variables. But for now, we're just going to do the expected value and the standard error and setting up these box models in the next half hour. So this is a probability model. It's a very simple type of probability model. And we're using it, we're going to figure out these statistics for these random variables, which are numbers, not just a list of numbers here. We're not going to do descriptive statistics anymore. These are variables. They're numbers that change, and they're generated by a chance process. So we're going to say what the probability of getting all the possible outcomes from this chance process are. What we'd expect to see, what the variability around that is, and then assign probabilities to each outcome. All right, so now there's an analogy between many chance processes and drawing numbers randomly from a box. This is going to be our simple box model. And adding their sum or taking their average, okay? In this chapter, we're going to translate gambling games, coin, dice, and roulette games into box models. Later, we're going to translate sampling processes, like polling, surveys, into box models. So a box model consists of a box with tickets, and on each ticket, you have to write a number on it. And then a specification of the number of draws to be made. So we usually call this n, is equal to the number of draws. And then we have to specify whether we're drawing with or without replacement. All right, and this is a big hint. In creating a box model, it's always simplest to start by making the box for a single draw. Think about what numbers need to go into the box for just one draw. Okay? Then, after you make the box, you think about how many times you're going to be drawing. So here's a good example. It's a very simple example. We want to create a box model for counting the number of heads in 10 tosses of a fair coin. Now, what's going to be varying? We're going to be counting the number of heads. Our random variable is going to be the number of heads. That's what it is, right there. All right, now a big hint is you draw the box for one flip or one toss. So here's a box. I'm just going to draw an actual box, and I'm going to have 2 tickets. And on the tickets, I have to have numbers. So I'm counting the number of heads. So on a single play, I could get a head or a tail, but those aren't numbers, H and T. So what am I doing? I'm counting the number of heads. So if I get a head, I'm going to count that head as 1 head, 1. And if I get a tail, I'll count it as how many heads? I've put a number on here. What should I put on? 0. 0 heads. So that's the idea. So there's 2 tickets in the box. Now, n is going to be, what is it, 10 times. So we're going to draw 10 times with replacement. So we'll draw 10 times with replacement. Why? Because if we drew, look, it will be depleted if we drew more than 2, and plus, we want the chances to be the same, 50-50 each time. We don't want the chances to change because we want to simulate flipping a fair coin. So draw 10 times with replacement, draw 10 times, so drawing 10 times with replacement, drawing 10 times with replacement, and taking the sum of the 10 draws is a way to simulate, simulates tossing a fair coin. And counting the number of heads you get. So for example, so right now we're going to look at what would we expect to get if we did that 10 times. Well, 5 heads, right? And then what would be the variability, the typical variability around that? And then for each one of those possible outcomes, like getting 0 heads, 1 head, etc., we'd have to assign a probability to that. And that would be, and we'd draw a histogram representing that. Okay? So, let's see, here's another example. Create a box model. So let's just note this up. Statisticians use the term random variable for variables whose numeric values are based on the outcome of a random process. In this example, the number of heads is a random variable with possible values ranging from 0 to 10, and each value has a probability associated with it. Like the probability of getting 10 heads would be what? There's only one way to get 10 heads out of 2 to the 10th. So it would be 1 over 2 to the 10th, or 1 over 1,024. Same with 0. And the most likely possibility would be getting a 5. And that's the expected value. All right, so let's create a box model for the number of 2s that appear in 20. Create a box model for the number of 2s that appear in 20 rolls of a fair die. What's the random variable? Well, what's varying? The number of 2s. And draw the box for a single roll, for one roll. So it's a die, so there's 6 ways it could land. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. So there's 6 tickets in here, and we're counting the number of 2s. We're counting the number of 2s. So we're not going to put 1, 2, 3, 4, 5, 6 there. We don't care. We only care if it's a 2. And if it's a 2, we'll count it as 1, 2. And if it's anything else, we'll count it as 0 2s. So that would be our box model. Another way you're going to see this written, just shorthand, is we'll still have 6 tickets here. But it's getting tedious to draw all those. So I'd just draw 2 tickets. One has a 1 and one has a 0, and then above it I'd write 1 of these and 5 of those. Okay? 5 zeros instead of drawing it all out. And it doesn't matter where you put the 1. You're going to be shaking this all up. It's a random draw from here. Shaking up all the tickets and drawing. All right, so let's move on. And now we're going to look at the expected value and the standard error. We call it an expected value. The expected value of what? The expected value of our sample sum. What do we expect our sample? If we draw n times, what would we, from the box, what would we expect our sample sum to be? It's going to change, so that's why we say the expected value instead of the average. So we're going to abbreviate this expected value, and that's standard error. So this expected value, this is like the average. It's an average for a chance process. So I'll say average for random variables. And this is like the standard deviation for random variables. It's sampling error. Every time you can think of it instead of the standard deviation, the sampling error. Like it's the error around your expected value, about how much you expect to vary around that expected value. All right, so let's look at this. So given a set of n draws from a box, we might be interested in lots of different statistics, but the ones we're going to look at is the sum of the draws. That's what we're going to be doing now, and that's relevant when you're gambling because it would represent your wins or losses, or the average of the draw, the percent of, like people who say yes to, do you think Trump should be impeached? And people who say no, something like a yes-no question. So these would be for polls or survey data, which we're going to move on to. But right now, we're going to look at this because we have a well-defined population. Gambling probability models can represent, we know exactly what's in the box, what's in the population, and we're randomly taking samples. Whereas with these polls, which we're going to look at later, we just see one, we take one small sample, and we're going to estimate what the population looks like. So it's very easiest to start off with a well-defined population, gambling, and then move towards sampling. So, okay. So the sum of n draws from a specified box will vary because each time that you draw n tickets, your sample changes, depending on the luck of the draw. So we need some way to quickly summarize the distribution of the possible sums. The average, what you'd expect on average, the sum to be, that's called the expected value, and how far off from that it's likely to be, the typical deviation from that expected value, the standard error. Later, we'll draw a histogram called a probability histogram, displaying all the possible sums that could occur when you draw n tickets from a specified box, and how likely the probability for each one of those. Okay, so it will look just like our histograms that we've been doing. And that will be in chapter 9. This is chapter 8. So the expected value, okay, so for n draws, so n, remember, is the number of draws. All right. So the expected value for the sum of n draws made with replacement, we're going to put it back from a box, is n times the average of the box. Do you remember what the average of a box is? The average of the box, so that's n times, this is the population. So it's times the population average, the average in the population, which we use Greek letters for, so we'll use that mu, n times mu. So we'll say mu is equal to the average of the population, which is the same as the box. All right, so 100 draws are made at random with the replacement from a box of 5 tickets. So in gambling, we have the whole population. This is the population. There's nothing else. Pretend we're just, that's our, we're just drawing from that box. All right, so mu, our average, is what? Just 4. So the sum of the 100 draws is computed. Well, think about it. The smallest the sum could be is what? What if we got all 2s? If we got all 2s, 100, this is n, so we'd have 200 if we summed them up. And the biggest is if we got all 6s. And then it would be what? 100 6s. So that would be 600. But what's the expected value? So the expected value of our sample is going to vary. Our sample sum is going to depend on two things. How many times we draw, which is n, and then it's not going to be, we're not going to draw the smallest each time. We're not going to be down there. We're not going to draw the biggest each time. On the average, we draw the average. So it's n times the average of that box, which is n, I'll say n times, just to remind you, the average of the box, which is equal to n. We'll use these Greek letters, and which is equal to what? 100 times 4, so it's 400. But, I mean, I don't think you really have to memorize that formula. It's pretty obvious that you're not going to get the lowest, the highest. You're going to, on the average, you'll get the average of the box and then however many times you draw. All right. So now, let's see what we're doing here. Okay, so let's look at this. You bet $1 on red 76 times in a row in roulette. That means that if the ball lands on a red, you win $1, and if it doesn't, you lose $1. So what is the expected value of your winnings? So there's our random variable right there, how much we're going to win either. So now let's just remember, this is really important. Draw box just for a single spin. I have a little roulette wheel, but I didn't bring it. So on a single spin, what can happen? You have this box. It would be like you either win or you lose. So you either win $1, that's one ticket, or you lose $1. That's your other ticket. Now it's gambling, and you're probably going to have more ways to lose, right? So you look here, and there's 18 ways to win the $1 if it lands on the red. There's 18 ways to lose and 2 ways here. So there's 20 ways to lose. And there's 38 slots altogether on the roulette wheel. This is true if you've played roulette. I should have brought mine in, but all you need to know here is that there's 38 slots, and if it lands in 18 of the reds, you win. Otherwise, you lose. So what's mu here? The average of the box is going to be what? Will be 18 ones plus 20 negative ones, which is -2 over $38. That's approximately negative a nickel, all right, on the average. So your expected value of the sum of your winnings when you play how many times? That's your n, 76 times, is going to be 76 times -2 over 38, which is -$4. All right. And now, any questions on that? That's actually a bet you can make in roulette. Now the standard error is a little more complicated. And this is a very famous law, the square root law. It says the standard error of the sum of n draws depends on two things. Again, this number of draws, each time you draw, your variation is going to be bigger, right? Times the spread inside the box. Now, we're doing standard error, not variance. If it was variance, if there were independent draws, it would be variance would be n times the standard deviation of the box. But we're doing the standard error, so it's called the square root law. So the standard deviation of the box, that's the population. We'll use the Greek letter. It's going to be square root of n times sigma. All right? So notice that as the number of draws increases, so does the standard error, but not as quickly. And so you can see I wrote a very simple proof for this on page 228 if you want to look at why the square root law. All right, so let's do an example. So again, we'll have this same box here where mu is equal to 4. And I'll just tell you sigma is equal to 2. You know how to do that. If you wanted, you just take all these deviations from, excuse me, mu is not 4. This is 5. Look at that, it's 5's in the middle here. I'm so sorry. So you take all these deviations, you'd square them, take their average, and then take the square root, and that's what you get. You can check it if you want. Now, compute the expected value and the standard error of the sum of 25 draws. So there is n right there. So what are we doing? We're taking the expected value. What do we expect our sample sum to be? Our sample sum is going to be n, which is 25, times the average of the box. 25 times 5, so that's 125. And then our standard error of the sample sum, we're not always going to get 125. We're going to get more or less than that. And the typical deviation is going to be, again, n, but it's the square root law, so you have to square root it. And a standard error is like a standard deviation. Standard error is a standard deviation. So it's, again, it involves n and the standard deviation. So times, I'll just say standard deviation, because standard error and standard deviation, this is for the, okay, these are very similar. So standard deviation of the population. So that's the square root of population. So that's 5 times 2, which is 10. So you'd expect the sum to be about 125, give or take 10. Okay? 125 plus or minus 10. Now what if you increase this by a factor of 4 to 100 draws? Well, this is going to go up by a factor of 4. So here you'd say the expected value of the sum is just going to be 4 times that, because you'd have 100 times 5, which is 500. But the standard error is not going to go up by 4. It's going to go up by square root of that. So instead of, now you're going to have the square root of 4 times 25. So it's only going to go up by 2. So you have the square root of 100 times 2, and that's 20. So you see how that just goes up by 2. So the standard error doubled in absolute terms. It went from 10 to 20, but halved in relative terms. What does that mean? Relative to the number of draws. So 10 over 25 is 40%, whereas 20 over 100 is 20%. So percentage-wise, it went down by the square root of n. All right. Let's now move on. All right, so now this is a quick rule for the shortcut formula. This is a shortcut formula for finding when you just have 2 types of tickets in a box. So for example, it's very useful when you have just 1s and 0s. So for example here, if you just have 2 types of tickets, what do you do? And again, you can see page 227 for the proof. So if you just have 2 types of tickets, how would you figure that out? Well, the difference on the tickets. So that's -3 minus 0. The positive, it's the absolute value, because standard deviation can never be negative, times the square root of, you have 10 tickets here. So it's the fraction of the tickets that have one of the numbers on it. So 5 out of the 10 tickets have a -3 on it, times 5 out of the 10 tickets have a 0 on it. So you can think of them as A and B. It doesn't matter which ones. Okay, so this would be what? 3 times, these are easy. I like to change them to decimals. It's just much easier to compute. And then you can see the square root of 0.5 times 0.5 is the square root of 0.25, which is 0.5. So this is 1.5. If you just have 1s and 0s on the ticket, then you just have the absolute value of 1 minus 0, which is 1, so you can forget about that. And then you have the 10 tickets. You have the fraction of the tickets that have 1 on it. So that's 7 out of 10 times 3 out of 10. So now another way to look at this is what? So you really have the square root of 0.7 times 0.3. So you can, another way to write this is P, the fraction that have the 1 on it, times 1 minus P. You'll see that all the time. It's the same thing. When you have 1s and 0s, you can forget about that, and you just say, oh, the fraction of the tickets, that's 0.7 times 0.3. So that would be the square root of 20.21. So it's a little bit less than 0.5. Okay, you can do that one on your own, and maybe we should just do this problem now. So a multiple choice test has 25 questions. That's your n. Each question has 5 choices, only one of which is right. So you're going to have 1 and 4 zeros. So if you get it right, you get a 1, and now all of these. The number of correct answers is what we're counting. That's our random variable. And so the expected value for that is going to be what? N times the average of that box. Mu is equal to 1 out of 5. So it would be n times 1/5, which is 25 times 1/5, which is 5. And the standard error would be what? The square root of n, which is 5, times the standard deviation. Now, what's the standard deviation times sigma? So the standard deviation of this box is equal to what? Well, we can use what we just said. The fraction of 1 minus 0 times 1 out of the 5 tickets, or 0.2, times 4 out of the 5. So that's the same thing as the square root of 0.2 times 0.8, which is the square root of 0.16, so that's 0.4. Okay? So that's 0.4. And so that's what? 2. Okay? Wow, how much time do I have left? I thought I was going to finish this, but I guess not. I guess this is a good place to stop because I only have what left. All right, so we'll start on page 51 on Tuesday. By the way, look, you know what a good thing to do? If I went quickly through here and you didn't understand this, look at the back of the book where I explain on page 227 where that formula comes from. And that is right here. And you'll understand it better.